Welcome to the episode on cohesion. Cohesion is a bit more abstract than the coupling mentioned this week, the name of which we do not translate into Polish. As we already know, cohesion and coupling often go hand in hand. They stand side by side in one definition. For example, when we talk about low coupling and high cohesion. In this episode, we'll look at the other side of the equation, which is why cohesion should be high, what it is, and how to measure it in our software. In my opinion, the definition of cohesion in our industry is too abstract. We say that cohesion is a measure of how individual functions that fall into one module are logically related to each other. Perhaps the definition in physics can tell you something more. In physics, what we mean by cohesion are intermolecular interactions, cohesion that is achieved through these interactions. Solids have high cohesion. We can also talk of cohesion energy, that is, the energy that is needed to break a crystal into free atoms, for example. You can apply this metaphor to the software world. If we have modules, classes, microservices with high cohesion, it takes a lot of work and a lot of energy to break them down into even smaller particles. We strive for high cohesion because such elements, modules, classes, microservices will have those things that should actually be next to each other. You could say that cohesion is a measure of how well we have subjected our system to the process of modularization. If we did it well, then we got a series of modules, each of which is characterized by high cohesion. What does this give us? Modularity, which is the element needed for extensibility. We can make changes quickly and at low cost. Speaking of changes, thanks to modules with high cohesion, things that change in business together within the space of problems fall into one place in our space of solutions, which automatically reduces the risk of propagating such a change. The change should be enclosed in one highly cohesive module. This is what we want to achieve. Also note that if we actually put things in one place, in one module, and those are things that depend on each other and change together, the bonds between the modules will be smaller. We will reduce them. High cohesion somehow makes coupling lower outward. You can see how these two definitions, these two concepts are complementary. As in the case of coupling, we have a number of types of cohesion. It is not worth remembering all of them. Let's say a few words about each of them. We ranked the types of cohesion from the least acceptable to the most acceptable. We have cohesion related to coincidence, i.e., coincidental cohesion, which says that two functions fell into one module, and that is all that binds these functions. There is no other business reason. Take utils classes, into which we put everything that doesn't fit elsewhere. They are characterized by coincidental cohesion. Logical cohesion is one that, it would seem, binds some logical entities together in one module, but when we look at it, it turns out that they have nothing to do with each other. For example, say we are representing an individual subscription and a corporate subscription in one class. They are completely different entities, but they have a common name. In both cases, we have the word subscription, so maybe we're doing it in one class. This logical cohesion does not really give us any benefit. Then we have temporal cohesion. It tells us that we have functions in a module because they must be executed at the same time. E.g., this may be a module that cleans up some threads or prepares some processes. In such case, we have to do many things simultaneously, so we group them into one module. Procedural cohesion. If the procedure requires a series of operations, these operations fall into one module for this very reason. For example, sorting that requires that data be first validated and then transformed to a different data format. We could create a module that encapsulates these three functions because we need them in the steps of our algorithm. Communicational cohesion tells us that in the module we have functions that use the same data structures. Sequential cohesion tells us that we have functions in the module, among which there is, for example, one that returns something at the output that the next one needs, etc. We create a chain of calls. In our field, in our subscription domain, it would be a module related to the preparation of the course for publication. First, we have validation. The validated course can be transported to the module or transcription function, and then for review. Functional cohesion. It tells us that the functions fell into one module because together they create a higher level business function. For example, If it were a calculator module, we would have addition, subtraction, square root, division, etc. functions. Someone might say that you can break them down into different modules. Yes, but these things together create a business function, which is why they are in one place. This is the most desirable cohesion. It's not that all cohesions are good or bad. The first two are undesirable, and we should avoid them. Somewhere at the stage of cohesion related to communication, we can already talk of cohesion, which makes sense. We cannot always achieve the highest level of cohesion. Basically, we should get modules that have high cohesion, and in which there are things that change together. Things that change separately were simply fenced off with other modules, and there is as little dependency as possible between these modules. As a result, any change should be closed in a smaller number of modules. Let us return to the example with the train. If the module was a railway carriage, then we still have some other distinguishable concepts in the carriage. There are seats or compartments, but if we change the layout or appearance of the seats, the entire carriage will be modernized. The change is propagated in one place. Let's see examples that are more relevant to our industry. A class that represents an individual subscription and allows it to be enabled, activated, disabled, deactivated. This class is characterized by very high cohesion. Why? Because it is responsible for one business function. It is responsible for the life cycle of whether the subscription is disabled or not. Someone might say, wait a minute, here I see two methods, and it would probably be easy to split it into two separate classes. Looking from a purely technical point of view, it is feasible. We can create classes. One is responsible for enabling the subscription, the other is responsible for disabling it. Note what the consequences are whenever we want to change, for any reason, the representation of the information whether the subscription is disabled or not. We just have a normal flag. Perhaps we want to have some type of enumeration, or this information is just hidden in 3 different fields. What did we get? We broke it down to a large extent, and now, every time such a change is made, we have to change 2 places, which gives us the logical coupling that we have already talked about. This change will be blurred over 2 different modules. Modularization has gone too far. Things that change together have fallen into different places, which means that we have approached the process of modularizing the structure of our software too granularly. A similar example. We can look at a corporate subscription that allows you to subscribe to it and unsubscribe from it. We can follow the same logic as in the case of individual subscription. These 2 functions are part of one big business function that is responsible for subscribing to a corporate subscription, and we are not going to split that into 2 different modules or 2 different classes for the same reasons. But if we add something to the corporate subscription class, and for example, throw something else there that refreshes the subscription, renews it, and payments, at first glance we speak the domain language after all. These are methods. There is encapsulation, there is some abstraction, and there are some implementation details which are invisible to the outside. Someone might say that now everything is fine. Just note that in fact, now all the things that trigger billing changes, subscription renewal changes, and enrollment changes are all concentrated in one class. This class has low cohesion. Changes to payments may cause enrollment or renewal errors. Although the class looks clean at first glance, we are actually dealing with a class with low cohesion. We shouldn't do this because we group concepts that change separately in one place. How will we know if any class has a low cohesion, lower or higher than another? Here you need measurable information metrics. The metric that deals with cohesion, or rather the lack of it, is LCOM, lack of cohesion of methods. It is about how methods, which are a contract of some class, together form a coherent class, a coherent unit characterized by high cohesion. Let's see an example with our corporate subscription, which, as we found, has a low cohesion. What's going on in the middle of a class like this? We have 3 fields and 4 methods here. The first 2 methods, enroll and withdraw, use the same field, enrollment. The next 2 methods, pay and renew, use separate fields, expiration date and payments. If we started to visualize this information using diagrams, we would get the following sketch. three fields: enrollment, expiration date, and payments. With sets, we can mark methods that use different fields. We have pay, renew, enroll, and withdraw selected. The non-cohesion metric tells us to first count the pairs of sets that are completely disjoint in this diagram. There are 5 such pairs. Pay is paired with renew. Pay is paired with withdraw. Pay is paired with enroll. Renew is paired with enroll and withdraw. From this, let's subtract all pairs of sets that have some common parts. There is only one such pair here, withdraw and enroll. 5(1) equals 4, low cohesion rate. Here we are looking for some more granular division into smaller classes. Let's take a look at a more optimistic case, such as an individual subscription we talked about: enable, disable, activate, deactivate. We have 2 methods and 1 field here. The visualization looks like this. One field is represented by a flag, and this flag is used by 2 different methods. Sets that have no common part and are completely unrelated to each other have 0. 0 minus 1 common pair that uses the same field. Mathematically speaking, we have 1, actually minus 1. This metric is normalized to 0. 0 tells us that there is maximum cohesion. There are little problems with this metric. The various tools we talked about this week when discussing coupling can measure this metric in different ways. It is worth seeing the documentation of the tool you are using. What exactly is counted there, so that there is no situation that we change tools and metrics also change. Moreover, this metric is not perfect. Let's take a look at 4 cases. Here, the dots represent some fields in the class, and sets are the methods that use the field data in our class. Intuitively, we can see that each of these 4 cases tells us that there are 2 different classes hiding there. But the metrics tell us otherwise. In the first case, we have a metric that says there is no cohesion, and there is one. We add some method to this class so that it uses the current fields, so it can be said to match this class. We increase the cohesion, and the metric does not move. We add one more such method, case 3, and this metric is already moving. What's more, it has dropped to 0, despite the fact that there are still 2 classes hiding there. So you can see that this is a good introduction to the conversation, but sometimes this metric will just not be perfect.